But the short punctuated fasts seem to be like, if your allostatic load is low, like, so your stress in your life is not, you're not adding stress on by doing a fast, then you can fast. Yeah. If you have a high stress load and then you add fasting, then you can end up with all sorts of like other metabolic issues.
Dr. Jacob Torres, your group just released a paper a few months ago, really interesting paper looking at time-restricted feeding and numerous effects of time-restricted feeding and a particular molecule that is produced through time-restricted feeding. I'll let you just go ahead and tell us a little bit about this study and what you found, because it's really interesting stuff, just how some of these results or some of these effects of time-restricted feeding and fasting can potentially be like replicated just by utilizing particular molecules. And
so you kind of summed it up. It's in the title of the paper, so it makes it easy to summarize. And it's if I remember properly, it's beta hydroxybutyrate recapitulates the beneficial effects of time-restricted feeding and fasting in polycystic kidney disease. So it's a long title, but it explains it, sums it up. And so what we did is we take we have a model, a study autosomal dominant polycystic kidney disease, or ADPKD, or PKD for short. And we took animals that have this disease and we put them on time-restricted feeding diets or periodic fasting, and we compared them head to head. So the time-restricted feeding animals are fed for 8 hours a day, and the rest of the day they have food restriction. And then the periodic fasting animals were fasted for 2 days sequentially, and then free feeding for 5 days. We compared that with, our readout is the disease progression. So we look at disease progression, and we found that both of the modalities they either halted the progression in the young animals, so they did not progress, towards, very late stage kidney disease, or in the adult animals, we found that they actually halted the disease or reversed some of the effects of the disease. So we look at things like fibrosis or kidney function, and those are diminished. So that was the main experiment. So we looked at that. And we were interested in how is that, what is the mechanism? Because we published back in 2019 a paper on ketosis doing similar effects. So that was using ketogenic diet. We had some fasting experiments, but we never really got to the mechanism of that. So this paper is the follow-up that then we took that, that experiment that I just described, and we compared that to just giving animals beta hydroxybutyrate, which is the molecule that's produced during fasting. And we found that had a lot of the same effects. It actually promoted a lot of the same signaling pathways. And we also were able to show that was effective in not only one model, but then 2 other mouse models. So we had been using a rat model, which we call non-orthologous. So it wasn't the exact human mutation. And then we did that in 2 mouse models that had the analogous or human mutation. So the polycystin 1 gene was mutated. And we found that beta hydroxybutyrate worked as well in those models as well.
So is there a translatable effect? So even if someone doesn't have, PKD, for instance, if they're watching this and they're saying, well, I don't have polycystic kidney disease, there's still sort of an overarching theme here of kind of an anti-inflammatory mechanism or something. Mm-hmm. And so that, there probably is something that's still translatable to people that don't necessarily have PKD, just for overarching research, or what would you say to that?
Yeah, that sounds about right.
I guess what I'm trying to say is,
what's the application? Yeah.
After today's video, I put a link down below for LMNT electrolytes. They are not sweetened with erythritol. LMNT electrolytes are 1,000 milligrams sodium, 200 milligrams potassium, and 60 milligrams magnesium. But that link down below gets you a free sample variety pack with any purchase of LMNT electrolytes. So whether you purchase their sparkling, whether you purchase their stick packs, or whatever, you get a free sample variety pack, and that's exclusively using my link down below. That is drinklmnt.com/Thomas. Again, drinklmnt.com/Thomas. Really interesting stuff. They curb my appetite entirely, but I also have them in a fasted state, and I sip on them during my fasted workouts because I feel like I actually get replenished, but I also get my cravings satisfied. So that link is down below in the description.
So PKD is a genetic form of chronic kidney disease. So chronic kidney disease is just our term for kidney function decline over time. So it's like the gradual loss of functional units of the kidney. So we call them nephrons. They're just these structural units. And over time, they become injured for various reasons. Different parts of them can become injured and they just die. And so you just lose that part of the kidney and it no longer has its filtering function. And if you can prevent the loss of nephron structure or function, then you can preserve kidney function, indefinitely. So everybody's kidneys are subject to injury because they're just, you live life, you eat food, you then cut through toxins. There's all sorts of different things that could happen. They get injured, and you don't want to have that injury kind of mount up over time. So if you can prevent just the slow, gradual, natural loss, and preserve kidney function, you can preserve health as well. So that's kind of the application outside of the disease.
So what I find interesting on this is, even if we flip it on its head for a minute, when you look at fasting, you have a lot of people that will say that, okay, the benefit of fasting is purely from the caloric restriction side, which definitely has merit. But with this, I kind of look at it as, okay, we're seeing a specific application for a molecule that is produced when you fast or when you're in a ketogenic diet, which to me kind of says, okay, wait a minute, it probably is more than just caloric restriction. Like there's something else going on. Some of this we could probably save for an entirely different topic, but like how much BHB, first of all, and I know this might sound a little like esoteric for people watching the video because not everyone is necessarily taking a ketone supplement, but like was it matched for the amount of BHB that was produced during a fast? Did you kind of equate for that? Or
no, I think if you were doing a full on, fast, like 2-day fast, I don't think you could supplement enough BHB to do that. We're talking about 100 grams or something during that time. I think for humans, it's a lot because you're getting 3-5 millimolar blood BHB. That's a lot of BHB being produced per day. There's no way you're going to take that as like a salt because there's just...
That would be GI distress.
Yeah. It would be a lot. Yeah, that would be rough. So, it seems like you could probably do 12 to 20-ish grams to get some of these effects that are happening. Like, cause it just, but you're only getting a short interval, right? When you take a ketone supplement, you're getting like a big spike of BHB and then it kind of goes away. But that seems to be like it does stuff, like it does have effects. And with the animals though, they're getting they're taking it all day. Like they're taking a little bit in all throughout the day. So it's not equivalent to the same as taking a big bolus at one time. It's more just like drip throughout the day and it still seems to work. So that's kind of the interesting thing as well, even though they're not taking it all at once.
What would you say a 2-day fast in rodents would likely equate to in humans? Do we kind of know what that math looks like?
I saw in millimolar or BHB being like 3 millimolar is what they get to by the end of the fast. And so humans are about similar, pretty similar. Yeah.
Yeah. I'd say if you're relatively low carb, you can get there pretty quick.
Yeah. And rodents are not the best keto model. Like I would not want to hang my hat on like everything that they do because humans are much better at fasting and using BHB and making BHB. Our systems are much more efficient at doing that. They're kind of they have a much faster metabolism. So the time they can fast is much shorter. They lose a lot of their body weight if they're fasting for too long. So it's not the best fasting system for that reason.
That's interesting. So it's almost as though like for looking at molecules and looking at BHB, they're not they might be decent, but when you're looking at body composition, stuff like that, you might see a lot more aggressive changes. So it's like not really fair to look at time restricted feeding in a rodent model because they can only go a few days without food ultimately, right?
Yeah, mice, it's like up to 3 days. I think then you probably would be to the point when you couldn't go any further. 2 to 3 days in mice is probably way too long already. 2 days is rough for mice because they lose a lot of their body. They're tiny and they lose a lot of their weight very quickly.
That almost makes it all the more interesting with this study, though, because then if you're able to recapitulate the effects of basically bringing them 2/3 to death with just a little bit, right? That's like, so it's like, okay, human, I'm going to make you fast for, 3 weeks or, whatever. It's obviously wildly, probably even longer. Humans can fast for a long time, but bring you to that 3/4 of the way or 2/3 of the way to death. To be able to recapitulate the anti-inflammatory effects, at least specifically in an organ system, with just taking like a ketone salt, that's pretty darn intriguing.
It is. I was intrigued.
So did you see blood ketones elevate much in the ketone application group?
So we had a couple different experiments. One of them was a water feeding experiment where we used a racemic BHB. That's like I think it was the Keto Force brand. It's like a sodium potassium blended BHB. So we could add that to the water and they could drink it ad libitum. That was the first experiment that we tried, and that one we could see a slight elevation in the DBHB. We actually measured both. We measured the D and the L, which is something that people don't do. They usually just apply BHB as if they do the racemic, they just look at the D and they don't look at the L. We were interested in both because the D is the version that we make through ketosis, and the L is the rarer version. We can make it. It's rare, but it doesn't have the same function because it can't directly be metabolized for energy. So,
interesting.
Yeah.
So do we convert D to L?
We make L from acetoacetate in a different way. Like it's a random draw that you can in a different pathway.
That's why measuring acetoacetate is kind of bogus anyway, right? Because it can be pretty random.
Well, acetoacetate has different functions too, and it's not directly equate. You need that to go into BHB, but acetoacetate is a little bit harder to measure in general. Like those
alveolar error or whatever.
Everything is it's more difficult to measure it. So people usually go with the BHB as the measurement. But LBHB, if you eat it, it kind of just makes its way through circulation and you pee it out. It doesn't have like a function the same as the D. I think it's produced at like times like heart injury. It can be produced for some reason. Like it seems like the heart makes it. That's one of the only cases I've seen that actually in humans where it pops up as like a metabolite. But if you eat it, it just kind of goes up and then goes down within a few hours. And so we measured that as well. And we can see that in the adult animals going up to like 1.5 millimolar in some instances. So if the signaling function of BHB is important, then LBHB is important because it will signal. So it has the function of the signaling portion of BHB, but not the energetic portion. And the D can do both, but presumably, it might be more dependent on its concentration. So it's kind of like, it's interesting because if you don't see the D going up, then you can assume that maybe its signaling isn't as important. But if the L is going up, then the L might be important for the signaling.
Interesting. Almost even organ specific or injury specific or something too.
Yeah, it's wild. Like the LD story is there's a lot of work to do there because it's just not highly researched. I think we're one of the few labs that's like actually, measured it and tested it and, like a system. So I actually one of the experiments I did was injected animals with D or L BHB and saw that they both had similar effects on the animal. Yeah. And so that was unexpected. I didn't know if it was going to work or not in that way, but it did look like they both had an effect and produced similar signaling effects.
Interesting.
When they were injected, but that was also very high concentrations of BHB.
So, that's in an injected form. And in this particular study, you could argue that a lot of the BHB is just kind of assimilated in the gut, right? It's just mainly just almost localized. Yeah, I would think that a lot the concentration of where the BHB ends up is probably higher in the gut than in circulation, just by virtue of ingesting it. Like it's just going to make its way through the entera before anywhere else. So it's been one of the big questions about like where actually the effect of BHB is located. Yeah, well, that's going to be my next question was like, are we seeing from your work and some of the other work that like it's really almost site specific? Like, if you're fasting, for example, and you're sort of marinating in ketones, it's almost probably hard to measure like all the implications, right? Like
the actual effect.
You're marinating in it, which is why like you can just generally say, okay, it's like, having an effect on, nuclear factor kappa B and this downregulation kind of overall, but it's like, what about like at local levels? It's kind of interesting. You see, like when you're ingesting it, you're putting it somewhere specific, right? So it's like, in essence, just by pure act of ingesting it. So then it's, has there been any work like looking at effect on LPS or anything like that?
I know that LPS, they have done some there are some experiments out there looking at the effect of LPS specifically with BHB. It should affect the inflammasome activation. I don't know how familiar you are with the inflammasome, the NLRP3 pathway.
I am, but I think for the sake of like consciousness,
everybody doesn't know about
gets into the weeds really quick. And I realized after I said LPS, I'm sure about maybe half the audience knows from me talking about it, but just in the essence of maybe just give a breakdown of gut inflammation really quick and how that works, and then this whole conversation. Sorry, guys, might make a little more sense.
Yeah, I know it's funny. So LPS. lipopolysaccharide is a component of the cell walls of certain gram-negative bacteria, and there's different forms of LPS, like the different types. It's a sugar-linked molecule, so it has different forms it can come in. But anyway, the innate immune system recognizes LPS. Every single cell in your body has a receptor for this compound LPS, and it activates the innate immune response, and then that has a cascade effect on that's the inflammatory response. So the innate inflammatory response is mediated by many things, and one of them is designed as LPS. So if you have bacteria that makes it into your blood that is pathogenic and releases this stuff, I mean, people have ever had food poisoning, they've experienced LPS sickness. Like they've had you get a big dose of LPS and it's just like you ache and you hurt and everything's terrible and fevers and the whole that's the inflammatory response at work. So if that stuff, it's constantly in the gut because there's tons of bacteria in the gut. So there's lots of LPS exposure in the gut that's always occurring. So there's a sensation in the gut that's like detecting LPS, like it's always there. So there's some amount that's required for like normal signaling. And some of that a little bit of that is always making it into the blood. And there's always like this little tiny bit. And that actually trains the immune system. Like it knows that there's this much LPS, and that's normal. And then you end up with things like gut inflammation, where you can have injury to the gut. The lining can become deteriorated, and then more of the stuff can make its way in, or you can just actually have barrier disruption where more LPS can come in. And that causes an inflammatory response as well. And usually it's localized. So you have something like IBS or Crohn's disease. Like you have these like local patches of inflammation that are, but then they can come breached, and then you have stuff that gets into the circulation, and that's what causes the global systemic inflammation.
Got it. So I mean, yeah, that explains why when people say the immune system starts in the gut. I mean, that's kind of like there's so much of this that and especially if I don't want to go too tangential here, but I mean, especially if people are, already dealing with some kind of inflammatory bowel disease, a lot of times they're more susceptible to other things just because they're already like at risk for that kind of leakage or penetration of the LPS.
So BHB interacts with the downstream effect of the innate immune system activation. So there's a complex called the inflammasome, which is it's a protein complex that comes together in response to the activation of the innate immune system. And BHB can actually block the activity of that particular complex. It's always kind of iffy about the exact mechanism. I think it seems like it binds to one of the particular components that blocks it's like a big crazy looking structure, and it kind of stops the activation of it. And so it stops the secretion of pro-inflammatory cytokines. So you make this stuff called IL-1 beta, and it kind of gets secreted into, outside the cell, and it goes to other cells and tells them to turn on their innate immune system. And BHB just blocks that pathway. So then those other cells don't get activated.
Yeah, it's interesting because when you look at the NF-kappa B data, like that's when people are like, they try to shoot down low carb or fasting. They're like, well, this is just going to happen with caloric restriction. But the NLRP3, that whole model, like you're actually blocking the secretion. I think that's where I'll just come out and say it, like some of the anti-low carb like people out there, like they don't look at that piece, right? Because we could do a separate topic just on inflammation in general, but I mean, the NF-kappa B and NLRP3 are two very different things. Like one is sort of a master regulator, like one is sort of this almost like first cavalry kind of like that comes out and you're actually blocking their release. So I guess what I'm saying is like there's an actual blockade versus just like the suppression of like a switch turning on or off, which can certainly happen with caloric restriction. The NLRP3 inflammasome sounds like it's directly mediated by BHB.
Yes, BHB has its little fingers directly in the NLRP3. That's one of it. I mean, that's one of its known pathways, and it also affects potassium efflux. So it has a little bit to do with the activation of that as well.
What is
so that's how the pathway gets activated, is that you have potassium leave the cell and then it turns on this pathway, and it seems like it blocks that as well. So it has like different mechanisms for affecting these two activations of it. It's interesting is that so BHB blocking this activation of the immune system, it's kind of I have to step back and say like, okay, is that good? Like, is that beneficial, right? Like, because your immune system I mean, it's relevant. It's the adaptive immune and the innate immune system are there for a reason. Blocking their activity willy-nilly seems not always like a good idea. So I have to step back and think of like, what's the evolutionary process that's like, why is it doing this thing? Mm-hmm. And so I think about BHB being kind of the metabolic sensor, right? So it's kind of the way of communicating the metabolic status to all the cells, right? So what's our current metabolic status? So if you're in a situation where food is restricted, then you're going to end up with, calorie restriction, free fatty acid release goes to the liver, you make BHB, and now the BHB goes to all the cells. And so now the cells are like, okay, we're making BHB, then that means that calories are restricted or food is restricted. So the immune system is the most costly system in the body. Like besides like the brain running itself, you have the immune system actually requires more work because and the amount of mass of cells you have to generate per day and the amount of maintenance they require is very high. So it makes a lot of sense that what the body would do is to come up with a way of preserving energy during fasting. So it's just suppress the immune system response so that you don't overcommit. Yeah. So you want to make sure that like this is a real problem that you're going to address because you need to reserve resources for real infections. So you want to tone down all of the little things that pop up because you don't want like a little bit of LPS to cause a reaction, like you're going to release cytokines to do this inflammatory response. If it's going to be like very costly, like you might have a big infection over here you got to deal with, and you're not making as many immune cells. You don't want to waste them all on this little cut you have or over here or some little non-issue.
That's interesting.
You actually want to reserve your capacity for more problematic things.
Do you think that with well, first off, I always get confused. Is it allosteric or allostatic when you're talking about just the general load on your body?
Allostatic.
Allostatic. Okay, yeah. Two very different things, but similar words.
Yeah, allosteria is when you have a protein and you have something nearby, a site nearby that modifies the shape of the protein.
Got it. Okay, so when we look at like sort of like our allostatic load, and that's just maybe our you got in a fight with your neighbor or you got getting divorced. There's like the load, right? Your overall I look at allostatic load as just like everything that's kind of happening in your life, right? And with fasting, it's like, is there, in your opinion, because I don't know if there's anything to look at this, I'm just curious to have this conversation. Is there a fine line between like almost fasting where you're just creating more allostatic load and actual fasting where you're having BHB produced? Because if BHB is sort of doing the blunting of this inflammatory response, then BHB could be somewhat responsible for the downregulation of the immune system if you're fasting too much, right? Compared to, say, just chronically reducing calories and putting yourself close to fasting, but to a point where you're not necessarily, or fasting for short periods of time where you're not actually producing BHB, but you're just stressing your body enough to suppress your immune system, right? Yeah. Are they two very different things, or do you think that I'm sure they work together, and I'm probably having a hard time putting this into words, but I just think about like from a recovery perspective, it's like, on one hand, it's like these shorter fasts allow you to get a little more calories in and maybe reduce the stress load, but like with a longer fast, then you get what I'm saying?
Yeah, it's like, is it beneficial fasting in the long term, or is it like calorie restriction beneficial in the long term? Like those are interesting questions. I think that like from my personal view of it, it seems as though caloric restriction has all these benefits, but the people that are doing it don't look well. Like this, just looking at the people who do chronic long-term caloric restriction, like they might be getting benefits by extending lifespan or whatnot, but I mean, they just are not, they just have deteriorated muscle mass and just, I don't know, they look gaunt. I've seen the examples of people that have been doing it for decades now. And it does not look great. Yeah. But the short punctuated fasts seem to be like, if your allostatic load is low, like, so your stress in your life is you're not adding stress on by doing a fast, then you can fast. Yeah. If you have a high stress load and then you add fasting, then you can end up with all sorts of like other metabolic issues, because it's just like your body you're just adding stress, because it is a stress response. You're going to get adrenaline and cortisol to go up. That's how you're going to release fatty acids. Like that's how it goes. Your cortisol goes up. If your cortisol level is already very high, you might not get a good response, and it might just be more stressful.
Yep.
So it's interesting with like BHB, because exercise also increases BHB. So one of the benefits of exercise likely is that it does the same, it has the same effect where it, we always talk about like it decreases inflammation, and it, does all this immune modulation. And it's likely, again, BHB pops up as that when you're doing, intense exercise for short periods of time, you get a really quick punctuated ketogenic spike during and following the exercise period. So it's like, it does seem like the punctuated BHB is kind of like necessary for your body to modulate itself.
Is there an inflammatory rebound sort of after BHB ceases, or is it more so an inflammatory rebound just by the presence of food coming in the first place?
It's a good question. Like, is the...
I'm mainly talking, because I think about like post-exercise, right? Mm-hmm. It's like if, you've got all this suppression of inflammation that occurs like while you're actually exercising. Right. Like, and that's why a lot of times you can say, for example, even when people are like a little bit sick and then they start working out and they're like, oh, I feel good.
You feel better.
You feel better because you're like, for a temporary amount of time, but then, the surge comes back afterwards, and it's just still like the post-workout sort of surge in inflammation that occurs. Hence why the ice baths right after workouts aren't usually good and things like that. So part of me wonders is maybe part of that is, this BHB blunting an inflammatory response and then sort of it rebounding.
Yeah, I wonder what that. Yeah, that's a good question. I haven't thought too much about the rebound effect of it. I always think I know when I'm not feeling well, I'll try to exercise, and that usually mitigates the symptomology. Like you don't feel like, if you have a runny nose or like you feel throat's a little scratchy, like we exercise normal, everything's fine, and then it usually just kind of subsides and goes away. Like you don't get that like long protracted illness. So it does seem like it might have an effect on at least preventing the progression of the inflammatory response or the progression of like illness. But it's required to have that recovery period, right, where like protein synthesis goes up and you have all, after the inflammation kind of goes away. So I think it's maybe there's probably some competing mechanism in there that of like anti-inflammatory during and then pro-inflammatory after. I mean, it's like you got to have one. They have to kind of balance each other out. I think you cannot have one side of the scale always pushed down. It has to be down to get homeostatic regulation to go back the other way. So I think that there probably is like a potentiation effect.
Yeah,
certainly.
Just a modulator, or a mediator, I should say. Okay, so if a lot of the effect, was potentially in the gut, does that mean that there's potentially a link between the gut and the kidney? That's because if we come back to like your, your core and where you were doing this work on PKD, it's like, okay, we're seeing BHB recapitulated the effects of fasting, particularly on PKD. So it's like if a lot of it's in the gut, then does that lead you to believe that there's a feedback mechanism or there's a communication there between the gut? I mean, it could be speculation, but what's your hunch on that?
So my original hunch, my hypothesis, so this is like current research I'm working on, is that the gut triggers the effect of PKD in the kidney. The reason I believe this is that we recently, we published a review article looking at triggers in PKD. So I had a postdoc in our lab, Melina Messing. She was the first author on this paper, and she was led the research effort. She had to do all the hard work of doing the bulk of the writing. I got to do a little bit of the writing, but that paper is really interesting because we look at the injury being more important than the genetic component ultimately. So the genetic component of PKD is that you have this gene mutation that then predisposes you to develop these kidney cysts. But what's interesting is that it seems the variation in the progression between individuals can be dramatic. Like people can be very fast progressing, requiring kidney transplant very early in life, and some people just never have an issue. They just live their whole life and never progress to renal failure. So there must be, it appears, that there's an environmental factor. There's something else going on. And so the research I looked before about oxalate in the kidney, that was our injury. Like that was one of the potential injuries, was that people are getting exposed to microcrystals in the kidney, and they're causing the injury response that then leads to cyst growth. And we think that the cyst growth is actually just aberrant injury response that doesn't resolve itself. So normally we think the tubules dilate in response to injury and that to clear things that are in the way. And then because there's that protein that's mutated is helpful in going back to normal, then it just kind of grows and continues to be a cyst. So if you can prevent the injury, then you can prevent the cyst formation. So one of the things we looked at was we're thinking that maybe LPS was important because it'd been observed a number of times that LPS would show up in cyst fluid, like these cysts are full of fluid. So there'd be all sorts of weird stuff in the fluid and inflammatory cytokines, LPS. There's been all sorts of weird stuff that bacteria end up in these cysts. So we were thinking maybe that it's that the injury in the gut causes transitive stuff into the blood, and that makes its way into the kidney and then interacts with the cyst cells and then causes a injury response. So the chicken and the egg is the problem though, right? Because it's like, okay, well, we also know that when the kidney gets injured, it has a difficult time filtering out a lot of the products that are metabolites that are produced, and they end up in the gut. So the gut kidney axis is like a big research area. And it looks like, as chronic kidney disease progresses, this is like where a lot of the research is done, is that you end up with dysbiosis. So dysbiosis is like a very, very normal progression of chronic kidney disease. And the reason is that as the kidney function declines, it needs to get rid of the urea that it's producing, and it just dumps it into the gut.
Wow.
So the gut takes this huge urea load, and then it changes the microbiome because it's now changing the types of stuff that's in there. And so some things can eat urea and some things can't. And so then the acidic environment is changing. And so then now you get this change in the microbiome, and then the microbiome, some of them make metabolites that injure the kidney. So they metabolize tryptophan and phenylalanine are the two big ones. And those can go into blood circulation because they're small enough to pass through the junctions in the gut, and they make their way into the blood, they go into the kidney, and they can injure the kidney themselves. So then you get a feed forward mechanism of more injured kidney, leaves more stuff in the gut, dysbiosis feeds back. But then that's like the normal example. And we're like thinking, well, maybe it's the other way where the gut actually is injuring the kidney first, and then that's what feeds forward towards the gut injury.
So is that where, like, is it true that if you have some kind of chronic kidney disease that, in this case, like tryptophan would be problematic? So would excess protein be problematic in someone with
That's
PKD?
been that's been the idea right behind they're saying like protein maybe is bad for that reason, because if you have, so transit time changes. So during, you have gut injury, right? So your transit time can either increase or decrease. If you have a lot of protein sitting in your colon, then there's anaerobic bacteria that can get a hold of that and do anaerobic fermentation on the proteins. And then those are called uremic toxins. There's different ones like the tryptophan metabolites and the phenylalanine metabolites. And then like TMAO is one of the other big ones that people are probably familiar with. Those all then make their way into circulation. So the idea is like, okay, you eat protein and then it ends up in your gut and it ferments. But really, it's just like you got to have a healthy gut and just assimilate it and push it through. So if you digest it properly in the upper GI, absorb it properly, it doesn't end up in the colon to ferment. So it's like, you eat a lot of protein. Just if your digestion is good, then you should be able to absorb that stuff before it ends up in the colon.
Yeah.
It's interesting, and that kind of confirms a little bit of your hunch, right? Where it's like if BHB is having an impact from an anti-inflammatory perspective in the gut, then maybe it's starting there. I could see how that, especially in like a later stage where protein could be problematic and you're limiting the inflammatory response kind of within the gut, and kind of that's an interesting thing. So you mentioned earlier before we were filming about how the kidneys really don't need much BHB to get the anti-inflammatory response. So even if it's and they actually produce BHB themselves. So is there a feedback or a forward feedback loop within the gut with BHB to tell the kidneys to produce a little bit themselves?
It's a good question. I don't know. I don't know if there's like a feed forward exactly. So in the gut, you're making these short chain fatty acid metabolites like propionate, acetate, butyrate, right? Those all have those all have immunomodulating effects, and they affect the enterocytes that line the gut. So they all do stuff, and then they can make their way into circulation, and then those have effects in the other organs as well. BHB it's not made as much in the gut. I know it can be made, but it's mostly the short chain fatty acids, because those are the bacteria that are making it. But it does look like BHB modulates bacteria in the gut. It modulates the immune cells and the enterocytes. But I think that's in a different context. That's like under ketogenic or ketosis context.
Gotcha.
In the kidney, so the kidney has the nephron it's like a tube. It looks like kind of like this, kind of like a U shape, and it goes back around, and then it kind of drains out into the bladder. So you have this glomerulus, and then you kind of go down and up and around. And at the beginning of the nephron, you have cells. They're called the proximal tubule cells, and those cells are very dense in mitochondria, and they contain the enzymes to produce BHB, but not to metabolize it. And they really depend on fatty acids. Because remember, these things are very energetic, and they're just pumping ions. Like that's their job all day is pump ions, and that's a very energetic process. So they make BHB. They can't use it, so that means that the BHB they're making is making its way into the tube, the nephron, and making its way around. And then there's distal cells, and these distal cells have the enzymes to metabolize BHB but not produce it. So it's kind of like this interesting little tube here. But what's interesting also is that there's this part where the two parts of the nephron connect to each other. There's like a little junction. And actually things can traverse back and forth between that junction. And BHB has a transporter at that little junction. So it can kind of go up and around and then come back through to the beginning of the nephron, like in a circle, like a loop. And it actually is with sodium. So it's a sodium transport. So it kind of exchanges sodium. So it actually increases the flux in the nephron. So it increases the flow rate of the nephron by pumping ions and BHB across. So BHB plays like a function just by increasing the flow in the nephron. It's independent of the pressure in the arterial, which is so you have the glomerulus is being fed by the blood supply, and the blood's being filtered through these little cells there, and then they kind of go into the filtrate in the nephron. And so BHB though is helping push that gradient of ions around, independent of the pressure of the blood.
Interesting.
So it's kind of an interesting part about this that's like, we see people's, like we have like a ketogenic dietary intervention, and we called Renew. And we frequently see people report that their GFR goes up, and they're like, why would your GFR go up when you go into ketosis? And one of the mechanisms is that you're getting better flux or flow through there. And we also saw something similar with the rat model as well. We could see that they clear creatinine better.
Interesting. Now, is that with that kind of ketogenic intervention, is that in particular like more traditional therapeutic ketogenic where it's lower protein, or is it just to aid the kidneys in that respect, or does that somewhat become irrelevant when you're on a ketogenic diet?
Well, we're keeping the recommendation is around 20% of the 20% of calories type of so it's moderate protein.
Yeah, which is not, by the way, not the same if you're doing it for body composition stuff, but in a clinical setting, that's pretty standard.
Yeah, so it's the moderate protein intake. Yeah, if your activity level is higher, you might eat more protein. I think that's as long as you can maintain ketosis, I think that's fine.
Yeah.
Yeah.
It's interesting. I mean, overall, it's that's really promising. And one, last question with this, does because people have access to ketone salts, like it's something that, but given that this is a very like potassium forward situation, does the kind of ketone salt, like salts are obviously bound to, ketone salts are bound to sodium, potassium, magnesium, or I think even calcium, right? Like I think that's kind of like what you're kind of, but it's, does that matter in relation with the kidneys in this particular kind of?
That's a good question. As I've seen, so the research on the different salts, so like calcium, magnesium, from what I've seen, they seem to be not as highly absorbed as the sodium and the potassium versions. The sodium, of course, has the risk of, too much sodium just being, a
lot of salt.
A lot of salt, yeah. But potassium, I mean, most people aren't getting enough potassium in general. So it's like the potassium salt's probably better for that reason. But the blended versions is great just because you're kind of spreading out the salt load over over the different ions. And then having sodium and potassium together is great because they are excreted together. Like that's part of their excretion. Like if you have too much sodium and you have enough potassium, you just will pee out the additional stuff without much issue.
Nice, man. Well,
yeah.
Where can everyone find you? And then also, I know you've got Keto Citra, which is something that you've worked on with your lab too. So where can everyone find you as well as that?
Well, they can find me at drjacobtorres.com and then SantaBarbaraNutrients.com. That's the company. We started from the research that I've done at the university. And that's Keto Citra is our product there. And the Renew program, we're starting that up again. So that's the ketogenic diet intervention that kind of combines all of our research that we've done, throughout the last decade or so, and then putting that into a program for people that's actionable. So it's all kind of together on that website.
Perfect. Right on, my man.
Yeah.
Thanks, brother.
Thanks.